Welcome to Chemistry at Hononegah High School, and today we'll be looking at PES, photoelectron spectroscopy. We're going to look at kind of a simplified view of really what really happens in PES. It's become an important part of the AP curriculum in terms of how do we know our electron configurations, 1s2, 2s2, 2p6, and so forth, that we talk about are valid. Well, one of the easiest ways to see it is with photoelectron spectroscopy. Now, this is what a photoelectron spectroscope looks like, and what's fundamentally happening inside that device. Now, this shows it as the incoming photons hitting a metal sample. In regular spectroscopy for different types of atoms, what we'd be doing is taking a stream of the gaseous atom and we'd be bombarding it with a high energy photon. So instead of hitting a piece of metal, which is really what we're looking at with a photoelectric effect, that we talked about earlier, we'd be using basically a stream of gaseous particles. So PES uses high energy electromagnetic radiation using the X-ray or UV light because you need to hit the atom with enough energy to literally knock out an electron from the atom to form a cation. So what we're going to do is we're going to look at and gain information about the electronic structure of a substance by doing that, by hitting atoms with these high energy particles and knocking out electrons. And then we're going to basically find out what the kinetic energy of that particle is. So you notice this talks about monochromatic. Well, basically what we're doing is we're taking one frequency of high energy radiation and focusing it through our sample. That's going to knock out an electron, goes through here, and then ends up hitting this multi-channel detector. And the purpose of the multi-channel detector is really to calculate the kinetic energy of that ejected electron that comes out, that photoelectron that comes out. We're going to use this device to really measure that kinetic energy. And with a greater understanding of what's happening with the energy of the incoming photon, we can use that to calculate the nuclear, or to calculate the binding energy, the energy that holds that electron. And we're looking at all of the different electrons inside an atom to the nucleus. Now, the first equation you see up here, X would be our gaseous atom. HV, well, HV represents that the energy of the high energy photon that's coming in. So that would be that incoming energy, which if we know the frequency, we know the energy of using the Planck's equation. And since we're knocking out an electron, electron is going to be one of our products, and the other product is going to be a cation. Well, what does this look suspiciously like that we've already talked about in the chapter? Well, if you go back to chapter 6, we talked about the concept of ionization energy, and this is actually similar to that. And once we have a better understanding of PES, we're going to come back to the concept of ionization energy and look to see how binding energy is similar in some ways and very different in other ways. But you need to have a little better understanding of PES before we get there. Now, first thing you need to get is that incoming photon's energy. You can't create or destroy energy in ordinary chemical and physical reactions, so that energy has to go somewhere. Well, the first place it goes is to break the force of attraction between the electrons and the protons. Now, this is basically our binding energy. Now, don't confuse this with the nuclear binding energy we talked about in nuclear chemistry in chapter 21. This is just the energy we have to provide to overcome the attraction of the nucleus to the electrons. Now, typically, this is going to be measured in megajoules per mole of reaction. So you'd basically be looking at the megajoules of energy needed to remove a mole of that particular electron. Now, one of the things that has a great effect on this, remember, is Coulomb's law. As the distance between the electrons and protons decrease, so we're going from the 2s energy level to the 1s energy level, the attractions increase by Coulomb's law, and the amount of energy necessary to break the attractions would then increase as well. So that's one important aspect of this situation. The other aspect is, if we have binding energy, what happens to the extra energy? So if we have more than enough energy to knock out that electron, where does the other energy go? Well, it goes to the same place we talked about with the photoelectric effect. It goes into increasing the kinetic energy of the photoelectron that comes out. So what we really have is a situation here where we know the energy of the incoming photon. So this is a known quantity. That's based upon the frequency of the X-ray radiation or UV light that comes in. We also then use the PES device to measure the kinetic energy of the ejected photoelectron. The only thing that's left then, with those two qualities known, or those two values known, is to calculate the unknown, the binding energy. So that's really how we get the binding energy. We take the energy of the incoming photon and subtract from it the excess kinetic energy of the emitted photoelectron. Do that subtraction and you have the binding energy to remove an electron from an atom. Now, when you take a look at this diagram, this is actually a simplified PES diagram, and what that simplified term really means is when we're looking at removing electrons from a particular sublevel, so let's say the two electrons that are in helium's 1s sublevel. Well, we have two electrons, and electrons inherently will repel each other. So really, to pull out an electron from that, you're helped by the electron-electron repulsions that are there. And when we have electrons with multiple sublevels, you may have certain situations where the removal of some of those electrons is going to be a little bit easier because electron-electron repulsion within an orbital. So what we really do is we take all those very similar binding energies and we lump them together as one binding energy. So that's why it's a simplified PES structure. And what you're looking at here is the PES structure for neon, which remember neon's electron configuration would be 1s2, 2s2, 2p6. Now some of the things you need to understand about this diagram. First thing is, what does the x-axis represent? Well, when you take a look at the picture, you see it says energy, and then it starts with 1,000. Remember, this would be megajoules per mole, and then 110, 1.1. So notice it's the reverse of how we would normally scale things. And you'll see why later it's written that way typically. And that actually represents the binding energy of the electrons that are coming out. So in this particular case, it looks like we in general have three different binding energies. Now, why do we have three different binding energies? Well, think about what each peak actually represents. The peak would represent the binding energy of the electrons in a particular sublevel. And in this case, we know for neon we have three sublevels, so one of these must deal with the 1s, one of these must deal with the 2s, and the other would be the binding energy to remove the 2p electrons. So fundamentally, the energy to remove any electron from that entire sublevel has been simplified to one energy term. Next thing you should understand about the diagram is that the y-axis represents the relative numbers of electrons, 1 or 2 or 3 or 4. So really, the height or intensity of that peak would represent the actual number of electrons at that binding energy, which would be the actual number of electrons in the sublevel then. Now, if you take a look at two simple photo electron spectrographs, this top one is for hydrogen. We only have one electron in hydrogen, and that's it, so 1s electron. And then in helium, we have two electrons, but you'll notice we still only have one peak, just like hydrogens. Well, that's because we're pulling them both from the 1s orbital. So for each orbital, we're going to have one peak. Now notice it's not really the height of the peak, so to speak. It's the relative height of the peak as it's described by the number of electrons. So this would be 0 electrons, the top one, that would be 1. This would be 0, that would be 1, that would be 2. So it's not look at the peak, oh, that means it's, a really high peak in the top one. That just represents one electron because we've only got one line there. But in the second situation, that's actually looking at the two electrons in the 1s sublevel. Now, another thing to notice here, and this is something you should be able to understand, is in this particular diagram, how come the binding energy of helium is larger? Notice it's farther to the left of the 1. That means it's a higher binding energy than the electron in the 1s orbital of hydrogen. Well, if you think about the nucleuses in each case, it makes sense why. In the bottom case, in helium, we've got two protons in the nucleus. And those two protons are going to have a greater positive pulling attraction on the electrons than in the 1s situation of hydrogen, which only has one proton in the nucleus. So this is related to the Coulomb's law idea about greater charge differences. Now, if we take a look at this photoelectron spectra, one of the things you should always be able to do first is identify what the element is. Now, don't try and figure out, is it 1s, 2s? Just count the number of electrons. Remember, these dashes represent relative numbers of electrons. So when you look, there's 2 electrons here, 2 electrons there, 1, 2, 3, 4, 5 electrons here. That's a total of 9 electrons. Look on the periodic table, what's 9 electrons? Well, this has got to be fluorine. Next, you need to be able to label the peaks. Now remember, I know the sublevel, which is the 1s that's closest to the nucleus, is going to have the highest binding energy. So that's going to be right over here. That is our 1s. And notice it's too high. Well, that makes sense. Fluorine is 1s2. Now the next peak here is going to be our 2s peak. And then finally, the last one here is our 2p peak. and it's got 5 electrons in it. So this would be the 1s peak, this would be the 2s peak, and this would be the 2p peak. Now, another thing you should understand about what you're seeing here is how come the 1s peak is so much further to the left? Well, think of Coulomb's law. The 1s electrons are significantly closer to the nucleus than the 2s electrons are. So for the same strength nucleus in fluorine, the closer electrons through Coulomb's law are going to have a much higher attraction, take a lot more energy to remove. So we would expect to see the 1s much higher in binding energy. Another thing to notice here is notice there's a bigger gap between the 1s and 2s than there is between the 2s and the 2p. Now, when you're looking at the 2s and the 2p situation, those are in the second energy level. On average, those electrons are farther away from the nucleus than the 1s electrons. And by Coulomb's law, that should mean they should have a lower binding energy. And the binding energies of the electrons in that same energy level, the second energy level, which are much closer to each other in terms of their average distance from the nucleus than those 1s electrons are, you would expect to see a smaller difference between the 2s to the 2p peak. And one thing that students often have a misconception of here, so I just want to highlight this idea real quick, is because the 2s peak is higher binding energy, they think, oh, that's because of Coulomb's law, it's closer to the nucleus. No, the 2p peak is actually on average closer to the nucleus than the 2s peak is. So how come it has a lower binding energy? Well, when you look at the radioelectron probabilities of the S versus the second level P, it looks kind of like this. So on average, the P is closer to the nucleus. But what happens is, this peak over in here, those electrons in the S penetrate much closer to the nucleus and shield those 2p electrons more, making the 2p electrons easier to remove, so lower in binding energy. So it really deals with what that graph looks like for the 1s electrons and where they're at, and that deep penetration that happens with the 1s electrons that shield those 2p electrons more. Next general idea here is I've put up fluorine and nitrogen side by side. You can see fluorine are the peaks that are the lighter purple, and they're shifted to the left across the board. How come? How come every peak for fluorine is shifted to the left? Well, think about it. Fluorine has a stronger nucleus than nitrogen does, so you would expect the individual binding energies of each individual sublevel to be greater. Now, I mentioned earlier it's important to understand how binding energy and ionization energy are similar but different. So now that we've understood these diagrams a little bit more, I think it's a little bit easier to see what's happening with these two ideas. So on the left here, I've got the orbital diagram for the carbon atom. And then on the right, I've got the PES spectra for the carbon atom. Now, one of the things you need to understand here is ionization energy is an energy needed to remove the first electron, which would be this one, from the atom. So the first ionization energy of carbon would be how much energy does it take to remove that electron? Well, that's actually going to be the exact same thing as the binding energy for those two electrons. Because remember, what we've got for binding energy is if we have all 6 electrons and we remove this one, how much does it take? If we have all 6 electrons and we remove that one, how much energy does it take? And essentially those two things are about the same energy, so it puts them together. Well, that's going to be the same thing as the first ionization of carbon. But you need to understand the binding energies of these electrons and those electrons have nothing to do. It's an apples to oranges comparison to the second and third and fourth ionizations energies of carbon, because when you've looked at the first ionization, now that electron is gone. And the second ionization would be how much energy it takes to remove this one. That's a completely different event than what's happening in our PES situation. We're looking at all of them still being there and we're removing any of the 6. How much energy does that take? That's completely different than the second and third and fourth ionizations of a substance. So the way in which they're the same, this binding energy should really be the same as the first ionization energy of carbon. But these binding energies would have no relationship to the second and third and fourth ionization energies of carbon. And last thing I want to remind you about is when they're asking you to justify or explain why things are happening here, don't forget a few key ideas. Remember, everything is going to be about the proton-electron attractions and the electron-electron repulsions. So in terms of proton-electron interactions, think of Coulomb's law, the number of protons. How does that affect through Coulomb's law? the strength of attractions and the binding energies. Also think about distance from the nucleus. So it's not only the charge difference through Coulomb's law, it's also the difference between charge centers. When you go to higher energy levels, you are farther from the nucleus. That decreases the attractions through Coulomb's law. And then also remember electron-electron repulsions can play a role here. Effective nuclear strength is looking at the difference between the positive pulling attraction of the nucleus as it is counteracted by the core electron repulsions that occur. And those are electron-electron repulsions that are happening in the inner energy levels. And that helps counteract or literally lessen the attractions between the protons and electrons. And the other thing to think about is electron repulsion that's caused by two electrons in the same orbital and how that affects attractions. Remember, when you have two electrons in the same orbital, there are repulsions there. And that first electron out of any orbital is going to be an energy advantage. And that can sometimes shift to the right your binding energies, making them lower than you think they should be. So sometimes those electron-electron repulsions, in particular, when you're looking at a repulsion in the same exact orbital on the same sublevel, that's going to actually help a little bit. So think of those things when you get to the homework. Hopefully this helps understand PES.